Hello, good morning. So let's start the class. So today we will continue our discussion on the shortest path problem. So last time we have talked about the Dijkstra's algorithm, and it is very similar to Prim's algorithm for finding the minimum spanning tree. Now today we will talk about these two. The first one is the algorithm when the input graph is a DAG, a directed acyclic graph. And then we will also talk about another algorithm called Bellman-Ford algorithm. So this algorithm has two authors here. One is Bellman and the other is Ford. But actually, this algorithm is developed independently by Bellman and Ford. And then for this algorithm, this time, we have extended the input so that we allow negative edge weights. So previously, all the edge weights are positive. It represents the distance like between the 2 points in a physical world, but sometimes we may have relationship between the vertices such that there are negative effects. So in such a case, then we may have negative edge weights. Okay, so let us go to the first algorithm, DAG. Okay, so but before that, let us recall the time complexity when we are solving the shortest path problem using Dijkstra. So if we use Dijkstra's algorithm, so we should have a time here. So the running time here is E plus V log V. So it is linear in the number of edges, but then for the number of vertices, it could be like there is an extra log V vector there. So if the graph has comparably similar number of edges and vertices, then in such a case, V log V could be the dominating part. So what we are going to do here is we are going to find a faster algorithm when the input graph is a DAG. Okay? So recall that if it is a DAG, then we can do topological sort of the graph. So the topological sort can be done either via using the DFS, or we can use the queue to help us to continuously, repeatedly remove the vertex that has no incoming edges. Okay, so there are two ways, common ways to perform a topological sort of the vertices in a DAG, and they are all running in linear time only. And then after that, what we are going to do here, okay, although it looks like yeah, a lot of text, but the idea here is that we are going to process the vertices one by one, starting from the left. And then by doing so, we can somehow use the dynamic programming approach to update a vertex and then find out what is the shortest distance from of a vertex from the source. So we will have an example and see what it means. Okay, so the difficult part here is just the topological sort. Once the topological sort is done, then we can process the vertex one by one from left to right and then update the distance or calculate the correct distance by using dynamic programming. Okay, so for instance, let's say this is the input graph, and let's say this is the source vertex S that we want to find, uh, the shortest distance from S to any other vertex. So what we can do here is we can first perform a topological sort like this. Now notice that the topological sort order may not be unique. So for instance, this blue vertex can appear after this purple vertex is also okay. But we can perform topological sort and use any one of them, it works, okay. And then we process, so first of all, we will see that for all, so there is a source vertex S, right? So for all the vertices that appear before S, then there is no way for S to go to that vertex. Yeah, because there is no edge going from the right to left direction. So if a vertex appears on the left-hand side of S, then the distance from S to that vertex is infinity because there is no way to do so. Okay, so what we can do here is we process the node and find that it is on the left of S, so we have infinity. And for S itself, it is 0. Is that okay? Now for all the other vertices, initially we just set it to be infinity because we don't have any information about whether this vertex will be connected from S in any way. But after that, what we can do here is we process the vertex one by one. So this is infinity. And then whenever we process a vertex, we can perform the relax operation. So we know that the distance from S to this vertex is correctly set to be infinity. So once it is known, then we know that there is a way from this vertex to S using 4 plus infinity, and from this vertex to the last one using infinity plus 8. So we can see that whether we want to update the value here and the value here. But because it is infinity and it is already 0, so there is no need to update the vertex here. So it remains 0, and it is infinity plus 8 versus infinity, so we just keep infinity. Okay, the next part is, so we perform relax. Okay, relax of this node. And after that, once we are done with the processing of one node, we move on to the next one. So this time we process the node S, and then we perform relax. By the time we perform S, we know that all the previous distances of the vertices before S is correctly set, so that S is also correctly set. And in that case, when we process this node, then we know that the distance from S to this one is 0, and it is a correct value. So we can perform relax. So there are two edges here. Relaxing S with this edge, we can update this to be 3. And then relaxing S with respect to this edge, we can update the purple one to 11. Once every edge connected from this node is already checked, we are done with this node, and then we can process the next one. Okay. Now when we process this node again, the value here is set correctly. And then we can perform relax. So the relax of this node is easy because there's just one edge. So we can relax this and then set this to be 5. And after that, we process this node and perform relax. So we set this to 11 and set this to 10 because 5 plus 5 is better than 11. So set this to 10. And after that, we process this node, but then this node doesn't have any edge, so the relax doesn't do anything. So we're done. And then finally, we are processing this node, and then it doesn't have any outgoing edge, so the relax is done. Okay. Okay, so the running of this algorithm is we first perform a topological sort. After that, we perform the processing of each node one by one. The total time for this one is proportional to the number of vertices, because there are that many rounds, plus the number of edges in total. So overall speaking, the total time is V plus E. So this is the total time. Topological sort linear time, we have relax operation, V plus E, so the total time is V plus E. And then why is it correct? So I will leave this for you to show the correctness. But the key lemma here is that by the time that the vertex V is selected, we select the vertex to process, the value inside it is already correctly set. And then this is the main point of this algorithm. Okay, so I will leave this for you. So if you understand everything, so this is already correct. This is simply a dynamic programming. Okay, so let me check if you are all okay with this so far. So far, so good, right? So if you have any question, yeah, please type it here. Okay, if not at this moment, let us continue with the next algorithm, the Bellman-Ford. Now, here we want to find out the shortest path from a source S to a certain vertex, and then the edges inside the graph may have negative edge weights. Now, first of all, we will realize that when there are negative edge weights, shortest path may not be well defined. For instance, why is it difficult, or why is it not okay to find out what is the shortest distance from S to V? So we see that if we walk directly from S to V, then we can have a length 4. But on the other hand, after walking to V, we may perform walking along this cycle. And the length of this cycle is -3 if we calculate correctly. So that by moving from S to V and walking this cycle once, then the total distance suddenly drops to 4 minus 3, which is equal to 1. And then if we further walk along this cycle another time, then the total distance will further drop by another 3, so it becomes -2, and so on and so forth. So the distance from S to V is now not well defined, because the more time that we are going to walk along this cycle, then we will have a further smaller value. So the problem here is that inside this graph, there is a cycle whose total weight is negative. So we call it, there is a negative cycle. So, or a negative weight cycle. So what we are going to do here is, okay, we are going to design an algorithm that checks whether the graph has a negative cycle or not. And if it doesn't have any negative cycle, then in that case, all the distances from S to a vertex, the shortest distance from S to any vertex, will be well defined. And in such a case, then we can compute what is the corresponding shortest distance. Okay, so if there is no negative edge weight, we can use the Dijkstra. If there is negative edge weight, we can use Bellman-Ford. And Bellman-Ford, this algorithm will tell us what? It will tell us the shortest distance when there is no negative cycle, and then it can also discover whether there is a negative cycle or not. Okay, so let's see how this algorithm works. So the algorithm is very easy. So don't worry about this graph, this part, because I can just simply tell you how it runs. Okay, so what we are going to do here is we are looking at a certain graph initially and set the shortest distance from S to itself to be 0. And then what we are going to do here is, in the first round, we are going to perform relax all. That means that we are relaxing each vertex one by one. So this is called one round. The ordering of which vertex to be relaxed doesn't matter. So we can perform relax this, relax this, relax this, relax this, and relax this. It's also okay. So there's no ordering about how we relax. But then when we've done relax all, this is called the first round. Is that okay? So relax all gives a new case, so that some of the values inside the nodes may be set to be non-infinity now. And then after that, we perform another relax all, so that we relax all the vertices in any order. And then after that, we perform relax all again, and also in any order. So how many times that we are going to perform this relax all? If the graph has n vertices, we perform n relax all. Okay, so or n minus 1 or whatever. So let's say n minus 1. N minus 1 vertices, then we will perform n minus 1 relax all. So in this graph, it has 5 vertices. So we are going to perform 4 relax all operations. So this is the scenario after the 4th relax all. And then we claim that, okay, by the time that we have finished all the relax all, then the distances are correctly set when there is no negative cycle. And then if there is a negative cycle, then we can find a way to check whether there is one or not. Okay, if you are okay, so let me double check if you are okay with this algorithm or not. So simply perform relax all many rounds. If there are n vertices, we perform relax all n minus 1 rounds. So normally, although we set the relax all to be in any order, so normally, because we are doing the same thing again and again, so we may be using the same order for each iteration. It's also okay. Okay. So first of all, we are going to check why this is a correct algorithm when there is no negative cycle. Okay, and later the other part is this part is actually checking whether there is something wrong, whether there is a negative cycle. Okay, so the idea of why this is correct is because if there is no negative cycle, then what does that mean? That means that between S and any vertex, there will always be a certain shortest path, right? So let's say the shortest path from S to V is going through using 3 nodes. Then in such a case, what does that mean? It means that the shortest path, okay, so the idea here is that after one round of relax all, if a vertex is of one node away from S in the shortest path, then the distance will be correctly set. Is that okay? So for instance, in this diagram, this is the initial diagram. So we will see that the shortest distance between S and this one is actually 4, because this node can get the shortest distance from S using one step. So no matter how you do relax all in this round, after this round, the value here must always be correctly set as 4, because this node has the shortest path from S using one step. And how about this node? This node has the shortest path from S using 2 steps, like 4 and then 3, right? So in that case, no matter how we perform relax all in the second round, because this node is already correctly set, so no matter how we perform relax all in the second round, by the time that we process this node, then the value here will be correctly set to be 7, the correct value. So we have a 7 here. Is that okay? And then the shortest distance from this node, for this node from S will be of length 3. 1, 2, 3. Am I correct? So we check this by eyeball. We see that it is 3. So although that it is not correctly set in the first few rounds, but after the third round, this node will be set correctly because of what? Because the shortest path is like this, and then the one that is on the shortest path before reaching this node will be correctly set in the second round, which is 7 here, so that by the time after the third round, we will correctly set to be 0, no matter how we perform the relax operation. And finally, the shortest path from S to this one, it turns out that it is equal to 4. Am I correct? So in such a case, like going through this, and this, so in that case, after the fourth round, this is also correctly set. So the basic idea here is that after the first round, all nodes with distance 1 in shortest path from S will be correctly set. And then after the second round, all nodes with distance 2 edge, okay, from the source node S will be correctly set. So that's why we will need to consider only n-1 rounds, because there is no negative cycle. So every vertex will be reached from S with the shortest path without any cycle. And then in that case, yeah, so n-1 rounds will be enough. So far, if you're okay with this, yeah, let me. Okay, so far so good, right? There's no problem. Okay. Okay, now the question here is, we somehow assume that the graph doesn't have a negative cycle. So what if there is a negative cycle? So let's see if we have an example. So in this example, there is indeed a negative cycle. But one thing that is nice is that whenever there is a certain negative cycle, so let's focus on this cycle, there's a negative cycle. No matter how we set the value, there will be something wrong after the final round. So why is it wrong? So let's see. So this is after the fourth round. Now because it is a negative cycle, so in that case, in that case, there must be a way that we start walking from a vertex and then back to itself using a negative value. And in such a case, we will have a strange thing to occur. We will see that for a certain vertex, in the final value, let's say this is minus 15, when we add the 1 here, so the value here should be minus 14. But what we are writing here is only minus 6. So what does that mean? It means that there is a way actually to go from this vertex with one extra edge to better improve the current value. And the reason that we can do so, it is because there is a negative cycle. It is the only way that we can make this even smaller after we have performed n-1 relax OR operation. So this is the case. So what does that mean? So this is the case that it will happen if and only if. Okay, so the theorem that it has here is that this is the something wrong lemma that we will see. Whenever there is a negative weight cycle, by the time that Bellman-Ford terminates, we will find that there exists some node v, which is the value with minus 6 in our example. It is greater than du, the distance of u, plus the weight that we travel from u to v. So there is a way to make improvements even after we have done n-1 relax OR, and it is impossible, right? So if this happens, then that means that there is something wrong. And the only thing that is wrong, it is because there is a negative weight cycle. Okay, so somehow you can see that this is the idea. You can prove this by contradiction. Whenever there is no negative cycle, this cannot happen. So if this happens, then that means that there is a negative cycle. Okay, so in okay, so overall speaking, what do we have? Okay, overall speaking, we have this is the result. It combines all. So whenever there is no negative cycle, Bellman-Ford works. And if there is a negative cycle, then we can find out something wrong. Okay, so okay, so this is the correctness theorem, if and only if. Okay, I think yeah, that's all for what I want to show you today. So Bellman-Ford is extremely easy to write. By the way, what is the running time? We haven't talked about this. This is about the correctness, right? Okay. So what is the running time of this Bellman-Ford algorithm? So can anyone? So let's see. Okay. So it performs n-1 rounds. So all the n rounds of relax OR. And then for each relax OR, we just need to check each vertex and each edge once. So vertices may be checked many times, but then we will go through each vertex and then check all the adjacent edges. So the time for one relax OR is v plus e, and then we perform order v relax OR. So the total time is order ve. Is that okay? Usually the number of edges must be greater than the number of vertices. Okay. So let's see if I have quoted the, I should have, and I must have quoted the time complexity. Did I? Did I? Oh, I forget to do so. Okay. So the Bellman-Ford algorithm. So you should be all okay by this point. It is order v times e. Okay, order ve time. Yeah, it runs. This is the place. It runs in order ve time. Is that okay? Okay. So that's all. Okay. That's all for today's class. Let me briefly mention about what we are going to do for the remaining part. So first of all, I'm still owing you the exam 2 solution. So I will prepare for it as soon as possible. And then we will talk about homework 5 and homework 6 solution. We will release homework 6 today. And then we will talk about homework 6 and homework 5 solution. And then we will also talk about something that is for your own interest. Okay, so let me go through the web page of our class web page here. Let me see. Okay, so this is the normal class web page, right? But then you can also go through our earlier web page, which is here, 2008. So this is something that I prepared to talk. So this is Bellman-Ford. So what I'm trying to talk about is I want to introduce something called the NP completeness on Friday or in the coming lectures, and also the so-called approximation algorithms there. So this is not going to appear in your exam, but then I think these are something nice that you should know, because it will usually appear in the in the in the graduate school entrance exam, or the if you want to apply for overseas university like those in US, then there is a certain exam, the GRE CS exam will have these topics. So I think it's nice to know about these two, but then we are not going to test you uh, during the exam. Okay, so that's all for today. Yeah, thanks so much for coming. Okay, if you don't have any question, yeah, let's meet again on Friday. Okay. Okay, so until then, see you. See you.